For our second project, one of the things we're going to have to do is pick out a pump that is going to work to meet our desired needs for our location that we've chosen. And so I want to talk a little bit about how do you select a pump. So here's a diagram over on the side here which shows the picture of the pump in the bottom underground in the water table, and then it's pumping water up into an elevated tank. And that's pretty much what we're going to be doing. We can use a different power supply. We're using solar or wind power. And what we have before us is pretty much a standard fluid dynamics problem, is to pick out a pump that's going to meet a set of requirements. So some things we need to know. We need to know what are the conditions at the intake of the pump underground, what are the conditions in the tank at the exit, and we need to know how much fluid are we going to have to pump in a specific amount of time up to that height. So when we think about where this is going to be located, we're looking at kind of remote locations where water is probably not the easiest thing to find. So probably the water table could be very deep underground. So one of the things we're going to want to use is a submersible pump, which avoids cavitation, which is basically when you're pumping water, you don't want to lose the suction, which is going to be drawing the water into the pump. So when you have the pump in the water, it doesn't have to worry about that. So if we look at the conditions that we have underground, the water really isn't flowing a whole lot, so it has a very low velocity there. Also in the tank, we're dumping the water into the tank, but the tank water is pretty much still, so we don't really have much velocity at the intake or the exit of the pipe. So those terms will be negligible. We also are going to be looking at the water. As you go down underwater, right, the pressure increases. So if you're under the water table a little distance, not looking at how far underground you are, but how far below the surface of the water table are you. There will be a little bit of pressure that the pump will see at the intake. At the exit, we're pretty sure if we have our pump exit at the top of the tank, we really don't have any pressure besides the air pressure, which will be considered negligible. And we also need to move the water from a low location underground to a high location at the top of the tank. That's our elevation change. And we need to know also how much water we're going to be pumping in a specific amount of time in order to meet our needs for our community that we're trying to provide water for. And that'll be different for everyone's location. We're going to have to use pump curves in order to properly select out a pump, because we need to know for a specific flow rate, we need to know how much head that we can achieve with the specific pumps, that we can get all the water up out of the ground in the right amount of time that we need to provide for our community. So we're going to use these pump curves, which are provided by the manufacturer, in order to properly select our pump. So how do we do that? How do we use these curves? Well, we're going to need to know what's called the system curve, which is going to be basically an equation that we're going to write. I'll show you the equation in a second, but it's going to be a plot on our graph. If we look at our graph here, the blue curve is the pump curve provided by the manufacturer of the pump. And then the gray curve is going to be our system curve, which is basically a curve of the required head that we're going to need. So as we increase the flow rate, we're going to have to increase the amount of head that we need in order to get the water up out of the ground to a certain height in our tank. And the point where they intersect is called the duty point. So where the system curve intersects with the pump curve, that's where that pump is going to operate. So we can determine at this duty point here, we can determine the flow rate, which is in 400 cubic meters per hour. And we can provide a head of around 42 meters in that diagram there. So a specific pump will provide a certain amount of head. We want to make sure that we're getting a sufficient flow rate and we're getting a sufficient amount of head in order to pump the water out. The volumetric flow rate that we want, Q, and the height rate distance that we're going to need. So we have to make a curve. In our case here, what we're going to see, these are some of the manufacturers for our pumps that we're using. You see these different curves here. This curve here I'm looking for this pump. The specific pump here is this curve, and this is my system curve. And I plot my system curve at different flow rates. I can see that it intersects right around here, so I can get about 10 gallons per minute with a head of around 320 feet or so. And that's an example of how we might use a system curve and the pump curve in order to select the pump to make sure it's going to be sufficient. So how do we get that system curve? This is the equation that we're developing. We're looking basically at the actual head that we're going to need. So we have our head terms. We have our pressure head, our elevation head, and our velocity head, and also the losses that are incurring that we need to overcome. So we do know that if the pump is below the surface of the water table a little bit, we're going to have a little bit of pressure there. H is going to be the depth at which we have the pump submerged below the water table. We're going to get a little bit of pressure there, but the pressure at the exit point of the pipe is going to be negligible. We also mentioned that the two velocities are negligible. The height change is going to be based on how deep is your water table and how high is your tower. And then our losses that are going to be occurring are a function of how fast is the water flowing squared. It's also going to be based on the friction coefficient in the pipes. There's a gravity term here. This is the diameter of the pipe, and this is the length of the pipe that we're flowing the water through. And we can find the velocity from the flow rate, that Q, which was on that graph, divided by the cross-sectional area of the pipe. So again, the cross-sectional area of the pipe is pi over 4 times the diameter of the pipe squared. So in the end, what you end up with for a system curve is this one here, that we have a height below the water table. We have a change in height of elevation between the pump and the water tower, and we have some losses there. And in order to determine how much power our pump is going to need, we have to provide a power supply for our pump. We need to figure out how much power we're going to need, that we can find out how much power is induced into the fluid by the pump by looking at, it's an equation there, which is the specific weight of water times the flow rate times the head that we're getting from that pump. And there are going to be losses too in the pump itself due to some mechanical movements going on and the water flowing inside the pump. There's some losses that occur. So the pump itself has a specific efficiency, which is usually a percentage, like maybe 80% or so. And we have to make sure we have enough power to overcome that efficiency, to overcome those losses. So the total power we're going to need to provide to the pump, we can find by taking this power that we have to put into the fluid and divide that by the efficiency, and that helps us determine how much extra power we're going to need to find our total power in order to select our power supply than using wind or solar energy. So that's a little bit about how we can go through some steps in order to select a pump, and there'll be more information that we'll talk about in class.